Welcome back to the channel. Today, we are conducting an informal journal club review of a fascinating preprint that was recently submitted for peer review. I actually found this manuscript because one of you linked it in a YouTube comment, and after reading through its conceptual framework, it warrants a serious discussion. The preprint attempts to tackle one of the most glaring observational tensions in modern astrophysics, the large-scale asymmetry of galaxy spin directions. Standard Lambda CDM cosmology relies heavily on the cosmological principle, the assumption that the universe is isotropic and homogeneous on the largest scales. If this is true, galaxy rotation should be entirely random. We should see a perfect 50-50 split between clockwise and counterclockwise rotating galaxies. However, recent deep field data from the James Webb Space Telescope, alongside large-scale surveys like DESI, suggest a statistically significant parity violation. Across vast cosmic distances, there is a preferred spin direction. Instead of attributing this to dark matter flow or cosmic shear, this newly submitted preprint proposes a radical but conceptually elegant hypothesis. What if this galaxy spin bias is a macroscopic imprint of holographic boundary conditions? To evaluate this hypothesis, we have to look at the foundational concepts the author is building upon. The manuscript operates at the intersection of two established ideas in theoretical physics: black hole cosmology and the holographic principle. As a quick refresher, the holographic principle dictates that the information within a 3D volume of space can be entirely encoded on its 2D boundary. Black hole cosmology posits that our expanding universe might actually exist within the interior event horizon of a much larger parent black hole. The author of this preprint asks a very specific question. If our universe is inside a black hole, and that parent black hole is rotating, what happens to the physics inside? A rotating black hole possesses an inherent angular momentum. Its 2D event horizon would exhibit a global chirality, a fundamental geometric twist. The hypothesis put forward in this paper is that this 2D boundary twist is directly responsible for the 3D galaxy spin asymmetry we observe today. But conceptually, how does a condition on the boundary of the universe dictate the rotation of a spiral galaxy billions of light years away? This is where the preprint introduces its primary novel contribution. Because calculating exact quantum gravitational dynamics on a cosmic scale is notoriously difficult, the paper introduces a conceptual toy model to demonstrate the mechanism. The author utilizes a boundary-to-bulk propagator, which they refer to as a smearing kernel. Instead of walking through the raw tensor calculus, let's look at the conceptual physics. Imagine the 2D boundary of our universe, not as a static wall, but as a dynamic surface possessing a built-in directional bias, a continuous chiral flow. The smearing kernel acts as a macroscopic projection lens. It mechanically propagates that 2D directional data inward, smearing it into the 3D bulk spacetime. Under this hypothesis, during the epoch of structure formation, the spacetime fabric itself carried a subtle underlying geometric constraint. As gas and dark matter collapsed to form galaxies, they weren't spinning in a truly neutral void. They were forming in a space that had inherited a preferred rotational bias from the boundary of the universe. In this toy modi, the galaxies aren't communicating with each other to align their spins. They are simply reacting to a dark sector-free geometric current hard-coded into the holography of our reality. Now, as with any preprint submitted for peer review, we must approach this strictly as a hypothesis, and the manuscript itself rightfully dedicates space to skepticism and alternative explanations. Before we rewrite standard cosmology, the astronomical community is still fiercely debating whether the JWST spin asymmetry is a true physical signal. The author notes that this parity violation could simply be an instrumental artifact. Variables like the telescope's point spread function, trailing arm bias in automated galaxy classification, or high redshift dust attenuation could be creating a false illusion of aligned spins. Furthermore, even if the galactic spin anomaly is completely verified, this holographic hypothesis must compete with local physical explanations, such as primordial magnetic fields or large-scale astrophysical bulk flows. For this toy model to transition from a theoretical hypothesis to an accepted physical framework, it will need to generate highly specific, falsifiable predictions regarding how this spin bias scales with redshift, which future Euclid and JWST surveys can test. Regardless of the ultimate observational outcome, this preprint represents exactly the kind of bold, lateral-thinking theoretical cosmology requires when confronted with new telescope data. It takes a real-world astronomical anomaly and attempts to solve it by building a conceptual bridge to foundational quantum gravity. I know this was an off-brand video in my channel, but it was worth helping out someone getting their hypothesis across. I highly encourage the physicists, cosmologists, and graduate students in the audience to read through the paper. Let's do some informal peer review down in the comments. Does this boundary-to-bulk smearing kernel hold up conceptually? Are there constraints the author missed? Thank you to the viewer who pointed this out. Subscribe for more deep dives, and I will see you in the next video.